We will continue with module 7 of this course on electronic systems packaging, and so far in this particular module the lectures that we have or the topics that we have covered included all the assembly techniques, and in the previous lecture we have seen the defects, or in other words the failures library have been extensively dealt with, and we also looked at lead free solder materials. So, today we are going to continue with materials issue and issues like thermal profiling that looks very important today in the industry when you are going to assemble thousands of boards, and there are certain entities like the substrate property, the component properties and the solder paste material properties, which together define the thermal profile. So, we are going to spend some time today on materials, phase diagram of tin lead, then the thermal profiles, different thermal profiles that can be set. This is true if you are doing even prototyping in your lab, and then for the industry it becomes a very large item that needs careful consideration by designers, manufacturers and the EMS, that is the electronics manufacturing services people, which includes the assembly sector. So, today's topics will be lead free material, phase diagrams, thermal profiles, and we will also spend some time on green electronics, that is materials that are banned in the industry, new materials that are being used by the industry today, so that it contributes to the green environment. The first thing that we are going to discuss today is the tin lead phase diagram. Although on the one hand we have been talking about phasing away lead and using lead free materials, but academically I would like to give you some information about the reason why tin lead has been used. In countries like ours, we still use tin lead. We do not have a complete legislation yet on the removal or banning of lead in our industry, but nevertheless our industry is also using lead free solder material to meet the requirements of end customers or for products that are being exported to other countries. So, if you look at a phase diagram, many of you are aware of what a phase diagram is. So, in this case it is a tin lead alloy. So, here on the left side you see 0% lead, and here you can see 100% tin. Okay. Now, if you look at mixing tin lead individual metals to form an alloy, and then if this phase diagram represents the mixing of the individual metals, and you can see that the solidus and liquidus portions of the tin lead material meets at 183 degrees centigrade, and that we call as the eutectic composition or eutectic melting point of tin lead, which corresponds to 63:37, that is 63% of tin and 37% of lead. This is the very common material that is being used in the industry for decades now, and the reliability of this alloy, solder alloy, has been well established. So, alloying is a term used for a melt combination of two or more metals. In this case it is tin lead. Now, what does alloying do? Alloying brings down phase transformation and therefore changes the physical properties like melting point, which is exactly what we have achieved by mixing lead with tin. So, the purpose of adding lead to tin is to reduce the melting point, because individually the melting point of tin and lead are very high. Okay. So, the main purpose of alloying is to reduce the melting point through eutectic or near eutectic phase formation. So, if you look at this diagram here, now here you see this is the melting point of tin, and here you can see 327 melting point of lead, and then when these two are mixed, there are various compositions that are obtained during the mixing, and obviously in the electronics industry 6337 is not the only composition that is being used. There have been compositions like 6040 tin lead, okay, and high lead content or high tin content compositions have been used by the industry for various purposes or applications. So, this is the liquidous phase, and then you can see this is bottom is the solidus phase, and then you can see various compositions being formed, and then the eutectic temperature is 183. Okay. So, this eutectic is 183. The composition here will be 6337. Now, there are impurities in the individual metals tin and lead. So, earlier it was assumed that 6238 would be the eutectic temperature, but because of the impurities added, it was later reassigned that including the impurities, which are very difficult to remove because they are in traces, 6337 is the ideal composition at the eutectic phase formation of the tin lead phase diagram. Now, the reason why I have put this number here is the atomic weights of tin and lead, and if you look at the atomic percentages of tin and lead, then it will be slightly different from the weight percentages. The 6337 that we are talking about is actually the mass weight percentage compositions of tin and lead. So, one needs to understand the tin lead phase diagram because if you are choosing alloys of tin lead in electronics other than 6337, you need to know the melting points which will definitely be higher than 183 for all other systems. Okay. So, here if you look at the importance of understanding the tin lead phase diagram and why we choose 6337, one of the studies that have been done over the years is that literature shows maximum shear strength of tin lead alloy at 6337 eutectic, because when you are talking about a solder joint, okay, using tin lead alloy, we are worried about the solder joint reliability. So, we need a joint that is highly reliable that can withstand various thermal cycles when the board is powered up, a printed circuit board is powered up, and when it is subjected to extreme conditions of operation. So, here you can see that at the 6337 the shear strength is at the maximum. That gives obviously a most favorable condition for solder joint formation. So, there are, coming back to this tin lead phase diagram, there are two things that we must know. You can look at weight percentage for interpreting the exact materials or the percentages of tin and lead, or you can simply look at atomic weight percentages of tin and lead. So, you will get different compositions. So, depending upon the package, so different packages use different tin lead alloys. it is not very universal throughout. A BGA package can have 6337 solder balls. It can also have 6040 solder balls. A QFP package which has got a FE-NI 42 base frame can have a tin lead coating or plating, okay, with composition of 6337 or 6040. In some cases flip chip we have seen they use high lead content 90 is to 10 percentage of tin. So, you need to look at the package data sheet to understand what kind of balls, solder balls, or what kind of plating has been used in the pins of SMD components or through hole components. This is very important because you are going to understand the effect of melting point, the solder paste melting point, and the substrate TG. All three are very important in deciding the thermal profile of your reflow process or your wave soldering process. Typically thermal profiles are very important for doing a reflow process. In a wave, obviously you are using molten solder for through hole components and a few SMD devices. So, this lecture we will focus on reflow process and the reflow thermal profile. So, what I am showing here is a temperature profile or a thermal profile in a reflow soldering process. Let us say IR soldering. Reflow soldering, as you know, are of three types, right. The first one could be by IR, the second one could be just by thermal convection air, and the third one could be vapor phase. We have seen all these three types of reflow soldering processes. Now, the atmosphere for reflow could either be just air or it could be done in nitrogen atmosphere. The influence of air or nitrogen in the reflow process goes with experience and goes with a careful study of the components that are used and the solder paste materials that is being used. Now, we are going to look in detail at this thermal profile and typically understand what are the zones in reflow soldering process. Okay. So, we are worried about the various zones that the board undergoes. Now, for you to recollect or recap at this stage, there is a printed circuit board which has been fabricated. It could be a high density interconnect board or it could be a double sided board or a conventional multi-layer board. Now, you are going to do reflow soldering, let us say in air. Okay. Now, the process steps for soldering would be applying the solder paste, right, pick and place the component, do a tacky cure at room temperature or at lower temperatures for a very short time, 5 to 10 minutes. Then you send it to a reflow soldering. Now, at the reflow soldering, the solder paste will melt, it will fuse with the component leads and then realign itself, so that there is no misregistration. The surface tension of the solder is good enough to pull back the component to its original coordinates. So, that is the process step for soldering. Now, in a typical industrial setup, when we do machine soldering, there could be various zones for reflow soldering. Now, if you look at this graph here, you will understand the various zones that are being used in a large volume setup. Typically, in a lab scale, you will have just one zone and you can easily finish the process. Of course, you can set the thermal profile for that single zone, but in industry you can have multi zones, okay, multi zones for reflow soldering. Now, you can see the terms here: preheat, that is a preheat zone, flux activation, or you can call it as a soak zone. Then you have the more important reflow zone, and then finally a cooling zone. Now, typically in industry, huge machines are available with zones perfectly defined. That means, the board will first go through the preheat zone, then the temperatures will vary for the flux activation zone, and then it will go into the more important reflow. It will attain the peak reflow at this stage, and then the board will be slowly cooled down to room temperature. Cooling should be a very slow process. You should not immediately remove the board after the peak reflow is done, because that will be a bit of a thermal shock. Therefore, cooling process also has to be well defined. Now, the terms referred here, okay, I will try to explain. We start with the room temperature, let us say 25, then it slowly moves to a predefined temperature, let us say that is known as the preheat peak minimum temperature and maximum temperature can be defined. So, typically somewhere here could be your first earmark for defining the preheat zone from room temperature. So, this could be typically from 25 degrees centigrade to, let us say, 150 degrees centigrade, depending upon your TG of the board. You want to activate the board, you want to activate the interconnects, the copper, and then you are also removing moisture from the components. Remember, we talked about moisture entrapment in capacitors, in BGA packages, in epoxy packages, and so on. So, when you are having such a situation where you might be having a large number of epoxy based packages or tantalum capacitors, ceramic capacitors, you want to remove the heat slowly, gradually. So, you do not want to hurry up this preheat zone. Okay. So, this typically should be done at 2 degrees centigrade per second, and you can have a preheat zone dwelling time of about 90 to 110 seconds. Okay. So, that is the kind of guideline that I can give you for preheat zone. Now, once the preheat maximum temperature has been reached, you now move into the activation zone. The important point here that you have to consider is activation zone will be crucial for the solder paste getting activated. Now, let me take your attention to the bottom of the slide, where I have talked about flux based soaking times. The solder paste contains flux, as you all know. Okay. It also includes some kind of an adhesive, because it helps in pick and place. It contains an epoxy media, and it contains flux. Flux is necessary for soldering, we have seen. It improves wetting, it prevents corrosion, and so on. We have also seen different kinds of fluxes in our previous lectures. So, the dwell time for soaking zone should be based on what kind of flux you are using in the solder paste. If you are using a low activated flux, then it is known as a low activated solder paste. The dwell time should be larger compared to a standard flux, where the dwell time is about a minute or so, and then if it is a highly activated flux, that means the flux in the solder paste is already activated, then you can reduce your soaking time. So, typically from, let us say, in this case 150 to a range where you are going to start the reflow process. Now, here this is the peak reflow, and this is the guideline that you need to have when the information like the melting point of the solder paste needs to be very clearly understood. Suppose you are using a solder paste which melts at 230 degrees centigrade. So, your peak reflow should hover around 230. Okay. So, ideally you would like to keep about 2 degrees to 5 degrees more than the defined melting point of the solder paste. So, typically your peak reflow in this case could be 235 degrees centigrade if the melting point of the solder paste is around 230. So, the reflow zone actually starts from here and then goes up to this point, right. So, the rate of heating will be different for preheating zone, soaking zone and the reflow zone. Reflow zone activity should be fairly less time consuming, because you do not want to expose the board, the components and exceed the temperatures that are defined for thermal shock of components and so on. Soaking zone can be large. Okay. So, typically from 150 degrees centigrade to let us say 210 or 220 can be a typical reflow profile for a solder paste which is melting at 230. Then from 210 to 235 can be your reflow zone. Soaking temperatures, like for example, it should be very slow, 0.5 degrees centigrade or 0.75 degrees centigrade or maximum 1 degree centigrade per second should be the heating rate that you should set in your equipment for the activation zone or the soaking zone. So, that your solder paste works up quite slowly. The advantage is that there will not be any solder bead formation, there will not be any spattering of the solder paste material, and you will have a very good activated solder paste ready to reflow. At this stage all the solvents are gone, the flux is activated and the tin lead is ready to fuse with your component leads. So, from 210 to 235 will be your reflow zone. This should be fairly fast, okay, 1.5 degree centigrade to 2 degree centigrade per second. And then you can have a very small residence time here at the peak reflow for about 5 to 10 seconds. Okay. In some cases it could be larger, and then you can start the cooling zone. So, cooling has to be gradual. You cannot immediately remove the board from the cooling zone and then try to finish your process faster. Remember, from 235 degrees centigrade to room temperature has to be done at something like 3 degrees centigrade per second or 4 degrees centigrade per second. So, the entire process you can expect from the 4 stages that we have defined: preheating zone, the flux activation zone, the reflow zone and the cooling zone typically should end in about 5 to 6 minutes. Okay. So, again we are talking about industry, we are talking about yield throughput for this machine. Therefore, even 5 to 6 minutes could assume to be a larger time, but again the industry people know better in terms of what kind of combinations of components, material and they are using. So, in any case in a reflow zone you can accommodate quite a few boards, okay, in a particular batch, and depending upon the conveyor belt size and so on. Therefore, it can never be less than 5 minutes. Okay. So, a process cycle typically takes about 5 to 6 minutes. So, this is what information I would like to give about what a thermal profile, because we have been talking about thermal profile for some time now, and you need to know very important issues regarding time for reflow, time for activation, preheating and cooling, and then the various temperatures that you need. You have flexibility in defining these points. This is left to you. As a designer also you need to understand this. If you understand this, you can interact with your assembly guys much better, and you can get a product that is a finished board in a much better reliable condition. Now, this is another thermal profile for reflow soldering. The earlier one, you can see the shape of the thermal profile is quite different, right. Now, here you can see that there is no residence time, there is a peak here. There is no residence time for the board that the board spends at the peak reflow zone. So, that depends again on your judgment of all the various parameters. Now, let us look at what are the zones here. On this axis you have the temperature, you have the time, time in seconds, temperature. Then this is the room temperature you are going to start with. Then this is the ramp up zone. Straight away you are ramping up to the soak zone. The soak zone starts here. Here you can see, compared to the previous slide, the soak zone is maintained at a particular temperature. Here temperature is constant. Temperature is constant for a particular time. Then the ramp up to the peak reflow starts. Unlike the earlier one where you had a residence time, here the peak reflow is attained and immediately it starts cooling. This is very useful when you have narrow process windows based on the melting point of the solder or the TG of the substrate or the type of flux that is used. In some cases, if it is a very reliable solder paste material and if you are very sure of the reflow process being done at a smaller window, let us say plus minus 2 degrees centigrade, then this kind of profile can be used. But if you are using materials which you have not used before, or if it is having low activated paste, then you want to keep more residence time at the peak reflow. So, these are the two basic thermal profiles that you can see in literature today, and you can fine tune it or change it according to your requirement. So, once again, here we have cooling typically, for example, 2 to 4 degrees centigrade per second. It is up to you to have a more dwelling time at the peak reflow, or you can go up to the peak reflow and then get back to the cooling zone immediately. And then here the most important thing, visible striking difference between the previous graph and this one is that the board spends a considerable amount of time in the soaking zone. Now, the important things anyway which you must consider for any thermal profiling is that look at the TG. Is it a low TG substrate or high TG substrate? Then you can fix your process window ideally according to that. Today most people are using FR4 with a TG of around 190 degrees centigrade. So, you have more flexibility in defining the preheat zone. Then the other thing I want to repeat, melting temperature of solder alloy that is to be used. In certain cases you have a problem. If you look at the entire bill of materials, your component list, there will be one component which says this component should not exceed 230 degrees centigrade for more than 45 seconds. The component is vulnerable to such a residence time during soldering. So, in such cases you have to be very careful in deciding the peak reflow or choosing the right type of solder paste for mounting that component, or if it is only a single component in the entire batch, then you can do a hand soldering of that component if it is feasible. Otherwise, these considerations become very important. The other thing is solder alloy composition and then the population density of components on your PCB. Remember, if you have a high density board, you can do reflow soldering. Parts of it can be done by manual soldering like your through hole connectors and a few through hole components, and you can do double reflow, that is, if you have double sided assembly, then the board can be subjected to twice reflow. So, this is the maximum generally as a guideline, as a rule of thumb. You can take it that a double sided board assembly can undergo thermal shock through soldering process twice. typically dual reflow, plus a few components that have been to be mounted by manual soldering. If you have to use wave soldering, let us say, then it could be one wave, one reflow, okay, or it should be dual wave for double sided if you have such a kind of a choice of components. If you have two reflow processes and then a wave, then it becomes too much of a thermal shock for the substrate as well as a few components. So, use your judgment in understanding the layout of your board vis-a-vis the assembly process. Now, what I am going to show here is a problem for us to work out today and see how we can understand, because I feel for designers this is a very important issue. Very often the board is manufactured and then you give your components to an assembly personnel in a EMS, and then if you do not interact with them on the subtleties involved, which will make a large count for reliability, then you have problem. Therefore, I like to spend a few more minutes on understanding thermal profile, because as a designer, if you can give this information to the EMS, then your board comes out well assembled. So, I will take a simple example. I will read it out. A PCB assembly has to utilize reflow soldering, let us say IR, or it could be thermal, that is not a major issue. The following details are available for the process. The process is not done in nitrogen atmosphere, that means it is done in air. Temperature in reflow zone can be plus minus 1 degree centigrade, okay. That is the kind of setting, because it is done in nitrogen atmosphere. FR4 substrate is used for this assembly and with a TG of 160 degree centigrade, and the PCB has a tin plating finish, right, not tin lead, tin plating finish. The solder paste with mildly activated flux is used in the solder paste alloy, that is a SAC 305 alloy. So, SAC 305 alloy is basically tin, silver, copper alloy, where the percentage of tin is 3 and copper is 0.5%, which has a melting point of 217 degree centigrade. It is a 100% surface mount device assembly. There are 4 high pin count BGAs, plastic BGAs that are used. Others are small outline ICs, passives, etc. The reason why I am giving this information is that if you have high pin count PBGAs, let us say there are 800 solder balls to be soldered, then you have to give more residence time, okay, for all the flux that is being used under the plastic BGA to get activated. You must also consider giving more residence time at the reflow zone, so that you will not end up with a plastic BGA where 30% of the solder balls are not at all attached or reflowed. Okay. So, make a point about this. The reason why I am giving this, in your board, in your system, you could encounter such day to day problems. The most vulnerable component among the entire components that are being used in this design can withstand 235 degree centigrade for 60 seconds only. So, that clearly defines your peak reflow zone residence time. It is recommended to have a one step reflow only. Okay. BGAs are large, that means if it is a double sided board, then one side undergoes a reflow, the other side undergoes another reflow process only. There is no other process involved here. BGAs are large, so that is also given here, 43 by 43 mm. So, draw a graph time versus temperature for the thermal profile and answer the questions below. Suggest start and end temperatures from room temperature to peak reflow. Mention heating rates in each zone including the cooling zone. Indicate board dwell times in all the zones. Okay. So, now we are going to work out this problem. Now, if you are going to assume this kind of a graph, okay, then what are the parameters that you can set? The first thing that if you look at the problem is that the vulnerable temperature for components is 235 degrees centigrade, right. Component vulnerability, we have seen there is a component which if it exceeds 235 degrees centigrade for 60 seconds, then it is vulnerable for failure. Therefore, you can keep the peak reflow temperature at 235, let us say minus 5 degrees centigrade, which could be 230 C. That is the first information that you can get. Then the solder paste melting temperature is known, it is given to you, that is 217 degrees centigrade. Okay. So, that information you have, right. Now, the peak reflow temperature time, because we have talked about the component. So, the peak reflow time can be kept as 30 seconds. Okay. It is a tight guideline process window, but 30 seconds is accepted. Now, the other things that you can consider is the ramp up rate in the preheat zone is what you have to consider now. Preheat zone is typically we can choose 2 degrees centigrade per second, first thing. The second thing is soaking zone or the activation zone. Here you can keep 0.5 degrees centigrade per second. Then the third one, to achieve peak reflow, that is to go into the reflow zone, you can keep it at 2 degrees centigrade per second, because if you look at the problem, it uses mildly activated flux. So, the soaking zone, it is fairly slow, but you can keep it for a longer time. Okay. So, this can be 2 degrees centigrade, although ranges are different, we have seen. Now, the cooling zone can be 2 to 4 degrees centigrade, but we will keep it as 3 degrees centigrade per second. So, these are the basic analysis that we have done. Now, so this is time, temperature, and here we can keep it as 30 seconds peak reflow, and this is 230 degrees centigrade. Okay. Now, the other one here, if this is 2 degrees centigrade per second, 2 degrees centigrade per second, then we can have this temperature around 217 degrees centigrade, then we can have this as 200 degrees centigrade, and then here it could be around 150 degrees centigrade. So, preheat zone, this is 25 degrees centigrade room temperature, typically could be if it is at 2 degrees centigrade per second. So, 25 to 150 degrees centigrade, this could end up in 62.5 seconds. Then we have the soaking zone or the activation zone, we said it is 0.5 degrees centigrade per second, right. So, this could be 100 seconds. These are ideal, because we have seen the conditions for this board. Then this one, the ramp up, which is at 2 degrees centigrade per second, this will be around 21.5 seconds. Then this is 30 seconds, we have seen residence time. Then you can create a window here, this one, this could be about 4 seconds, and then the cooling takes place at 3 degrees centigrade per second. So, this will be over in about 64 seconds. So, if you add up the total time requirement from start to finish could be about 275 seconds. So, less than 5 minutes, the entire board is going through the various zones including the cooling zone, and then we can expect that the flux is activated properly, the solder paste is melted completely because of the volumes involved, especially a plastic BGA which is used. And in this particular problem we are talking about 4 such plastic BGAs of a large size, that is 43 by 43, and this is a good guideline. Okay. So, you can work on this problem, and if you have any other suggestions as to how you can improve this total time and the temperature definitions for the various zones, you can work out and then get back to me by email. So, this is one situation that we have worked out. Now, the other problem that also I would like to, if you are looking at the same problem using the other thermal profile. Okay. So, here again various same considerations, the Tg is 160, okay. Then the melting point is 217 degrees centigrade for the solder paste. Then the vulnerable component thermal shock is at 235 degrees centigrade for 30 seconds. So, now you can start from the room temperature, the same conditions apply. You are going to give more preheating or soaking zone time. So, you can keep typically about 125 to 160, let us say 160 could be your temperature. So, from room temperature to 160 you can go at a heating rate of about 2 degrees centigrade per second. This could be 2 degrees centigrade per second. Then the soaking time you can keep it for longer time, 0.5 degrees centigrade per second. At 160 you can keep for a longer time. Then from 160 if you set the peak reflow to 225, there is no residence time as such. So, from 160 to 225 is your ramp up time at the rate of, let us say 2 degrees centigrade per second, 2 degrees centigrade per second. Then your cooling zone typically again 3 degrees centigrade per second. So, 225 to 25. So, if you calculate the times accordingly, you will get the total time. Okay. For each of these you can calculate the time, and then totally you can get the time taken for reflow if you are using. The only difference that you see here is the Tg of the board is 160. So, you are utilizing that temperature to ramp up in the preheating zone. So, from room temperature, then at 160 because you are also talking about the flux. So, this could slightly be changed. You can split this soaking zone into 2 zones. Okay. So, from 160 to 180, 190 you can have a quick ramp up, and then from 190 to 225 you can have the reflow ramp up. So, that could be modified. So, you can also consider modifying this zone based on the information that we have. So, this is also workable because you are trying to activate the entire system at 160 degrees centigrade, and then you are moving from 160 to 225 without a residence time, and then getting back to room temperature gradually. So, typically this also you should end up in about 225 seconds, sorry 225 seconds, which is less than 5 minutes and acceptable for the industry process. So, the underlining point, the takeaway from these 2 slides that I have talked about is that there is no consistent thermal profile or a universal thermal profile. It depends on the system that you are using. So, look at all the issues carefully, look at the problem that you have in terms of components, substrate and paste, and then draw your own thermal profile do a trial run 3 to 4 times on a board, look at the solder joint, examine the solder joint visually, and then go ahead if it is a mass production. So, what I intend to do now is give you a homework problem. So, look at this homework problem. The entities are slightly different here, the temperatures are different here, and then you can also try at home how to arrive at a thermal profile for such a system, and then you can email me or post your comments on the web. Now, getting back to some more basics of the solder system. If we talk about tin lead, there is always an intermetallic layer that is formed. If you talk about a system like this, okay, this is copper. We talk about base metal in a PCB. This is copper. This is, let us say, tin lead solder material. Now, this is what happens when you do soldering. Solder gets attached to the copper, and once that alloying happens, the intermetallics are immediately formed. As the temperature increases, the intermetallic layer thickness also increases. Even at room temperature, over a period of time, the intermetallic thickness grows. So, initially there will be a particular phase or a composition or a compound, and if the board has been used for a longer time, let us say, and if you analyze the layer thicknesses, there will be difference in the thicknesses. That is because the intermetallic growth phenomenon is continuous, and if it is done at higher temperatures or if it is subject to higher temperatures, the growth rate is very high. That is why I have put this graph here to show typically temperature versus microns per second growth rate, and you can see for copper it is, this is the temperature. So, as we move up the temperature, we can see the growth rate for copper fairly high, gold, silver, palladium, platinum, and so on. We have also seen in our earlier class that when you have copper and if you want to plate gold on copper, you need to have an undercoat of nickel to prevent diffusion of gold into copper. So, the intermetallic properties are dependent on the alloying system, the plating, the base metal and the plating that it takes, and the multiple coatings that normally we do with the printed circuit board cross sections. So, typically in a printed circuit board you will have base copper, then you can have a nickel gold coating on which you can do a soldering process done for components. So, then you will have much more complex intermetallics that could be formed. The only thing is the gold can prevent a diffusion of tin lead into copper. But if you look at this picture here as a cross section, what it says is basically at the area close to the base metal, you will have base metal rich compounds. What are the base metal rich compound interfaces? Typically Cu3SN. Then on the solder side, you will have solder rich compound, typically Cu6SN5. Cu6SN5 is solderable, Cu3SN is brittle and non-solderable. That is why you have to make sure that the soldering process is done on a clean copper surface, and if you try to repeatedly do desoldering and soldering on the same surface, you will not get a wet joint because of the different intermetallic layer that is formed and which is not amenable for soldering process. So, intermetallic growth is common in all solid state systems. It is caused by solid state diffusion of one metal into another metal's lattice structure. The rate of diffusion depends on the crystal structure of each of the metals. Therefore, you have to solder as quickly as possible. use lowest possible temperature that yields acceptable joints, avoid repeated soldering. This will increase the thickness of the intermetallic layer, as I told you. Any board, any system which is having tin lead, if you repeatedly solder, desolder and repair your components, the reliability is going to go down. Intermetallic layer growth takes place at any temperature, even at room temperature and at lower temperatures, and at high temperatures, nevertheless, as I mentioned, it is faster. Some of the common electronic solder alloys and their designations will now be discussed. So, we have seen tin 62, lead 36 and 2% of silver added normally to reduce the melting point from 183 to 179. This has been in practice for surface mount device assembly for a long time now. You get a very good joint, more wettability, more mechanical strength to the component leads, and it has a much better appearance and finish. So, the common one is 6337, okay, which includes impurities of course. Then the melting point 183 used for through hole components, SMD, hybrid devices and so on. I talked about 6040 is also possible. Melting point range is 183 to 191 used in SMD and hybrids. Then you have some uncommon solder alloys like tin is 96.3, silver 3.7, melting point 221. This is high melting lead free material. So, if you are using system away from the normal eutectic, then you have to look at your thermal profile in a different way. I also talked about the possibility of high lead content, low tin content, temperatures are very high, some BGAs and flip chip bumps have been manufactured before the ROHS legislations. Even today I assume that certain packages, very few in number, are still being allowed to use this because of the reliability issues and so on. So, again 97.3% tin, C4 flip chip manufacturers have been using that. So, temperatures are very high. Okay. Now, of course, C4 flip chip are available with lead free materials, and this is another such example from the literature that we have. So, academically this table gives you the various compositions of tin lead, silver that have been practiced in assembly. Now, look at best alternatives for lead, because now we are moving away from lead. We have to look at alternatives for lead. So, the best thing or the best bet would be SAC 305 alloy, and in some cases people are using SAC 405 alloy. Now, what is SAC 305? SAC 305 indicates that there is 3% silver in that and 0.5% copper, and the remaining percentage, that is 96.5%, is tin. So, it is a more tin based. Lead is removed and replaced by silver and copper, adopted by the Japanese and then but being synthesized by major solder companies, and it is available in India, elsewhere, and is being extensively used for SMD assembly. The other one is SAC 405 alloy. So, here you have about 4% of silver, 0.5% copper, or they say some literature gives it as 3.9% silver and 0.6% copper, and the remaining 95.5% tin, adopted by NEMI, that is the National Electrical Manufacturers Initiative of US. So, silver provides mechanical strength. So, why do we use silver? It improves the resistance to fatigue from thermal cycles. The use of copper in this alloy, it lowers the melting point, improves resistance to thermal cycle fatigue, and improves the wetting properties of solder. In some cases, tin has been alloyed with bismuth. So, tin bismuth alloys are known. It might be prohibitive in terms of cost and in terms of application. Bismuth might not be a good choice, but in certain cases it is acceptable. It lowers the melting point and improves the wettability. Tin indium alloys are known, expensive though, lowers the melting point and improves the ductility. Zinc, if it is used in any of the tin alloys for lead free, lowers the melting point and is low cost, but it is susceptible to corrosion. So, you do not want to really use that. Antimony is added to increase the strength, very small percentage. So, these are the best alternatives for lead free solder. So, lower melting point lead free solder alloys, most of them melt at higher temperatures than tin lead. To lower the melting point, use indium or bismuth, possess better rework and repair characteristics. For example, if you talk about indium as the component in the tin lead free alloy, tin is 48%. You can see the melting point is very low, quite low, lower than the eutectic tin lead, useful for temperature sensitive components. So, this is the ideal requirement or application when you are using this, because today in certain electronic products, the components that are being used are sensitive to higher temperatures. Cost and availability is a problem. Bismuth alloys, you can see the melting point is 138, quite low. The percentage of tin is 42 and bismuth is 58. Cost is comparative to tin, but it creates brittleness and poor fatigue resistance. The disadvantages are reduction in wetting property and special flux is required. So, there are advantages in using lead free alloys like the lowering of the melting point, but at the same time if you look at the bottom line, you have problems in terms of the reliability, in terms of wetting, fatigue, resistance and so on. And obviously, there have been some applications where these are used, but they are more special in nature. So, we will continue with the lead free alloys and then move into green electronics. We will discuss some of the issues that are affecting the electronics industry globally in terms of material choices for green products.